the 3D coordinate system. So we typically have been working in R2 with X and Y, and now we're going to add a third dimension. So here is the coordinate system. You can see that we have our x-axis here. This is positive x, negative x. We have a y-axis here, positive y, negative y, and then we have a z-axis, positive z, negative z. And here is our xy plane then, and this is what we were typically used to graphing and working with in 2 dimensions. And now we have an xz plane. If we look along the x-axis and the z-axis, and we also have a yz plane. And this divides our 3 space or 3-dimensional space into octants. There's 8 of those, so we call them octants. And the first octant is right here where we have positive x, positive y, and positive z. You can think of that as the room. Down here in the bottom corner is the origin, and then we have our positive axes here, and here is our first octant. So then if we went behind this door, we'd get the next octant and around and so forth. And if we went down in the basement, we would, where the z's were negative, we would have the other 4. This is called a right-hand coordinate system, and this shows you why. If you take your right hand and you point these fingers where the x and the y axis would go, then it would show you where the z needs to go, which the positive z. So let's look at first here the yz plane, which is right here. So now let's look at x equal 3, and if we move this plane along here what we're doing is we're making a restriction on x has to be 3, so we moved out 3 here, but there's no restriction on y and z, so it's a plane parallel to the yz plane at x equal 3. Similarly, if we looked at the xz plane and we wanted to have a plane parallel to that, here's an example, y equal 3. We could move out 3 in the y direction, and x and z are unrestricted, and so we would need to include all values for x and z, and we would get this plane parallel to the xz plane. And if we wanted z equal 3, first we could look at the xy plane. X and y are unrestricted, take on all values, but we would move up to where z equaled 3. When we want to represent a point, we use what's called an ordered triple then, and so just in the order x, then y, then z. So as we go to plot x, we would move along the x-axis. Here's a positive x moving by a, and then what we would do is we would move parallel to the y-axis to plot our b. So we come along parallel to that by b, and then we would move parallel to the z-axis from there to plot our c. So here is our point A, B, and C. So it's often useful too, as you just move along parallel or sometimes make a little dashed line to see where we are as we go to plot this point. So let's look at another one. If we wanted negative 4, we are going to move where x's are negative, so that's going to be back this direction. And then we want a 3 for the y, so we're going to move parallel to the y-axis out 3. And then the z is negative 5, and so we're going to go down instead of up. And it's often helpful to make some kind of a dashed line to help us see. We need it parallel to that line, so we go down 5, and there's our point. You can see as we do this, here's our 3-dimensional, and if it's helpful to do that as we move along to get parallel pieces, we can do that. So here we have some points, and you can see that some of these are on the different planes, and let's look at our point P right here, which is our point A, B, and C. We're going to talk about the idea of projections. Now, a projection would be if you just were looking on a certain plane. So if we take this point P and we actually moved it down and put it at Q, this is called the projection of P onto the XY plane, because the XY plane is down here, and so we took that point, and if we had, you can think of it like we shined a flashlight above, and where would the shadow be? Down on this floor here, or this XY plane, and it would be right here at Q, where we had our same XA and our same YB, but the Z was 0. Similarly, we could look at a projection of this point P onto the YZ plane, and so we would need to keep Y and Z the same, but our X would be 0, so it would move back here to point R. And we could also project onto the XZ plane. So here is our point. Think of if we had a flashlight out in this direction so that we're shining it and looking at the shadow onto this XZ plane, which is right here, and you can see that it would be over here at point S where we had the same X and we had the same Z, but the Y was 0. Now we call this space three-dimensional, or R3. And if we wanted to sketch a surface, here we have the equation y equal x. Notice there's no restriction on z, but we are in R3. So we could plot this y equal x, and on the xy plane, if we projected it down onto the xy plane, it's just going to be a line where we move out 1 for x and 1 for y, 2 for x and 2 for y, and so forth. And we would have this line, but then we need to include all z's, and so it would turn this into a plane. So let's look at an example here to see what these graphs might look like now we've added the third dimension. So we want to find all the points x, y, z that satisfy these two equations. So this one does not have any kind of requirement on z, but here is the other piece of where z will be. So let's look at this first. X squared plus y squared equal 1 would be a circle on the xy plane, but then the second restriction says we need to move it up to where z equaled 2. So this would be all points on this circle of radius 1, but is shifted up 2. So what if the restriction was x squared plus y squared is less than or equal to 1? So we would want this circle, but then we would also include all points inside of this circle as well. And then this restriction is the z is anywhere from 0 to 2, so we would need to start down here and include all of the z values up until 2. So this would describe a solid three-dimensional thing. This is a cylinder, but includes all of the points inside the cylinder as well as the surface of the cylinder. So in 2 dimensions we had a distance formula. It was based on the Pythagorean theorem. We took the change in x squared plus the change in y squared, and that would be the distance squared. And so we could then, square root, and we had the distance formula. So the distance from point P to point Q is, here's our distance formula. Now in 3 dimensions we can do a similar thing. So we could look at this projected down onto the xy plane, and we would see that if we had our change in x and our change in y, then we could have this piece right here, which is the leg of the three-dimensional triangle. So this leg would be our difference in x's squared plus our difference in y squared square rooted. And now if we had that and we included this leg, we would have this leg, which is our change in x squared plus our change in y squared, plus this leg, our change in z squared, and then square rooted to give us this distance. So here's our distance formula for 3 dimensions. You can see the analogy adding one more dimension. So our distance formula in 3 dimensions. We've got our difference in x squared plus our difference in y squared plus our difference in z squared square rooted. Now, if we look at a circle, we have the center of the circle at AB, and then we have a radius for the circle to give us a point on the circle, and our definition of the circle in 2 dimensions, or 2 space, is all of the points that are equidistant from AB that are r away. So we could make some radii, and if we did this for all radii around here, we would define all of these points on the circle. And our equation of a circle is based on the radius of the circle. If we did the distance formula here, we would have x minus a squared plus y minus b squared square rooted would equal r. And if we didn't want the square root in there, we could square both sides, and that's how we came up with the formula for a circle. This is something you should already be familiar with. Well, we could have an analogous thing in 3 space, or 3 dimensions. We could have a sphere, and we start with the center at ABC, and we have a radius and get a point on the sphere XYZ, and we could look at various other radii, and all points that are equidistant from ABC, that are r away in this case, but in 3 dimensions, would build this sphere. And if we wanted an equation for the sphere, we could look and use the distance formula and have the r would equal the distance between these points, which would be x minus a squared plus y minus b squared plus z minus c squared. And then if we didn't want the square root, we could square both sides, and we now have the equation for a sphere. And you can see again it's analogous to the equation for a circle in 2 space, but now we have our third dimension here. So here we have the equation of a sphere. Now, if we have what we call 0 dimension, we have a point. If we have 1 dimension, or it's also called r, we have a line. This is when we just used x and we got like a number line. If we add another dimension, 2-dimensional, we call it R2, we would have this plane or build things in 2 dimensions here. And if we added the third dimension, then we have R3, and we can look at this represented like a cube. Now, there are such things as higher dimensions. They are harder to imagine, harder to illustrate, but they do exist. And for example, in the 4th dimension, this is called a tesseract, and very interesting when we add that 4th dimension. And this is a tesseract as we are changing just one axis and moving things along one axis. So you can see as we start entering multidimensional world, it makes things very interesting. If you move on to Calc 3, you will work with multivariable calculus, and we will work with 3 dimensions or sometimes more.